then discuss the convergence of Jacobi and Gauss Seidel. So the convergence, last lecture we studied a little bit like why it, in what cases it converges, right? And one of the views about its convergence is for the case where the matrix is diagonally dominant. We have already seen that for Jacobi iteration, my iteration is basically xk k plus 1 at index I is basically equal to minus 1 over aii, the diagonal entry, times so let me assume I'm solving ax equal to b, right? Then what I'll be doing is then it's gonna be minus bi plus summation of j not equal to I of ij times x j k, right? So that's like when you look at the Jacobi iteration at the ith row, that's what it is. Previously we looked at the example of a simple equation where the off diagonals are just the two ones, and this aii is minus 2, right? So you ended up having the summation of aij divided by minus of aii is simply an average in that case. But like if you write out a matrix, it's this form. So it's if you have the exact solution, you can do the same analysis of the error in the discrete form. So I can write down the converged solution for x without a superscript k. This is going to be satisfied exactly. And then if I subtract them, I get e, the error, is equal to this without this b, because the b cancels out. Not equal to I, aij times ej to the k. So now it's pretty obvious why this Jacobi iteration is going to converge if the matrix A is diagonally dominant. So if aii is greater than the summation of aij, where j is not equal to I, the diagonal entries dominates all these off diagonal, dominates the sum of the off diagonal entries. So this is called the diagonal dominance. Okay, then we can see that this is the absolute value of eik plus 1 is less or equal to a summation j not equal to I, aij absolute value divided by aii absolute value of ej of k, right? Absolute value. So this is a summation with weights that sums up to be less than 1. All right. So if for example ejk has a maximum value, so let's say ek, let's define this to be the max over j ejk. So then this is going to be less or equal to summation of course I can replace this ej of k with the index with the maximum among all the k's. So that gives me ek, right? And if A is diagonally dominant, this summation, right, is less than 1. So this is strictly less than e to the k. So that means the maximum value of the error over all the indices I or j is going to decrease for each iteration. Of course, it'll converge, right? So that's the diagonal dominant case. And you can follow the same argument, show that for Gauss-Seidel, it'll converge even faster. Because for Gauss-Seidel, it'll converge faster if I'm diagonally dominant, because what actually happens for Gauss-Seidel? For Gauss-Seidel, you have less things on this numerator and more things on the denominator, right? You have more terms in the implicit part and less terms in the explicit part. So for Gauss-Seidel, under the same condition, it'll also converge and converges faster.